All right, ready to dive deep.
Always.
Today, we're tackling a concept that's more than just a physics term. It's the driving force behind so much in our universe. Momentum.
I like where this is going.
We've got excerpts from, let me see, a university physics textbook chapter right here.
Yeah.
And I am so ready to break down this fundamental, really, truly fundamental concept with you.
You and me both. What I find fascinating about momentum, is that it goes way beyond equations, way beyond. It has real-world implications everywhere you look.
Okay, so we've all heard the phrase momentum thrown around, right?
Okay.
But what does it actually mean in the physics world?
Okay.
When I think of momentum, honestly, I picture a runaway train.
Oh.
Like that feeling of, oh no, it's unstoppable.
Yeah.
Am I on the right track there?
It definitely captures the essence, yeah. Momentum, at its core, it's about an object's mass, how much stuff it's made of, and how fast it's moving.
Right, it's velocity.
Exactly.
We remember that.
So it's a measure of how much kind of oof something has when it's in motion.
Oof, like that.
A runaway train, it's got huge mass, right?
Yeah.
And considerable speed, so that gives it enormous momentum. Makes sense.
Okay, so following that, then a tiny pebble, that wouldn't have much momentum.
Right.
Right? I mean, unless
Yeah.
we launched it out of a slingshot or something.
Exactly. Even a small object, even a tiny little pebble can pack a serious punch if it's moving crazy fast. Think about it.
Yeah.
A bullet.
Oh, right.
Tiny,
Yeah,
but deadly.
because it's going so fast.
High velocity equals significant momentum. And you're right on with the slingshot analogy. That's exactly what it does. It increases the pebble's velocity, which boosts its momentum significantly. In physics, we describe this relationship with a simple formula.
Hit me with it.
Momentum, which we shorten to P equals mass m times velocity v. So P equals mv.
Okay, elegant and straightforward. I like it.
Right.
So it doesn't have to be big to have a big impact. It's all about the combo of mass and velocity.
Exactly.
Okay, what about something like, a baseball player hitting a home run?
Okay.
The textbook uses that as an example, but I'm not, totally seeing the connection. Help me out here.
Okay, picture this. The baseball player, they use their entire body to generate force, right?
Yeah.
They swing that bat.
Oh.
That force is transferred to the bat, and because the bat has mass and is moving with, you guessed it, velocity, it now has momentum.
Okay.
When the bat connects with the ball, bam, it transfers some of that momentum, sending the ball flying.
So it's like a chain reaction of momentum.
Momentum transfer in action.
And a heavier bat, because it has more mass, would have more impact.
You got it. And a faster swing. Even more momentum, even if the bat isn't as heavy.
So both strength and technique are key.
That's why they get paid the big bucks.
Yeah.
It's all about generating that maximum momentum.
This is making me look at sports in a whole new light. Seriously. Okay, let's talk about the other end of the spectrum. You mentioned a runaway train, but what about something massive that moves really slowly?
Okay.
Yeah. Like a super tanker?
The super tanker.
It's in the textbook, too.
That's a fascinating one because it highlights the impact of large mass on momentum. Even though it moves relatively slowly, it's huge, right?
Yeah.
So that sheer size means it's got an incredible amount of momentum.
So trying to stop it quickly is,
Good luck.
nearly impossible.
You would need an enormous amount of force to counteract all that momentum.
Okay, I'm starting to see how this momentum thing is everywhere. We've gone from baseballs to bullets to massive ships, and it's all connected.
Right.
Now, is this momentum thing only for objects we can see? Or does it go even smaller, like the air we breathe?
You're onto something there. Momentum, it's not just for the big, impressive stuff. Even the air we breathe, which we kind of take for granted.
Right.
It's filled with these tiny, microscopic gas molecules. And guess what? They have momentum, too.
So you're telling me those little, invisible particles bouncing around all over the place, they're following the same rules as a giant supertanker?
You got it. Each molecule, they're incredibly small, but they still have mass.
Right.
And they're constantly in motion, bumping into each other, bouncing off surfaces.
Yeah.
And all those collisions, trillions of them every second, that's what creates the air pressure we feel. It's like this whole hidden world of constant motion and momentum. Crazy. Right?
Okay, that is seriously wild. It's blowing my mind over here. Now, I got to ask, what happens when these objects, whether it's like a baseball, a supertanker, or even a tiny little molecule, what happens when they collide?
collisions.
That seems like where things get really, really interesting.
They're a fascinating window into how momentum works in the real world.
I mean, talk about messy, though. Think about like a meteor smashing into the
Oh,
Earth,
yeah.
creating a massive
It's
crash.
right there in the textbook. Collisions, they can be dramatic.
They can. Or even just, like, have you ever seen those slow motion shots of a tennis ball hitting a racket?
Yeah.
It's like, whoa, a collision right before your eyes.
Exactly. And, those collisions, they illustrate a really key concept.
Let's hear it.
Impulse.
Impulse. Okay.
It's not just about the momentum itself, it's how that momentum changes over a period of time.
Okay, so give me an example. How does that work with the tennis ball and the racket?
So the longer the racket's in contact with the ball, the greater the impulse, and the greater the change in the ball's momentum.
So a longer, more powerful swing from the tennis player equals a faster moving ball after they hit it.
Exactly. It's like they're giving their momentum a boost. And this principle of impulse, it's crucial for so many things.
Like what?
Think about like designing a car
Oh, okay.
for safety. Those crumple zones, at the front and back,
Yeah.
they're designed to increase the time it takes for the car to stop during a crash.
Oh, that makes sense.
So a longer collision time, it actually reduces the forces involved.
So it's kind of counterintuitive.
But save your life.
Wow. Okay, so understanding impulse, it's not just theoretical. It has like real-world life-saving applications. Okay, so going back to these collisions, they seem kind of chaotic.
Yeah.
But is there any order to the chaos? The textbook mentions this thing, the conservation of momentum.
Ah, yes. Conservation of moment. It's huge. One of the most fundamental principles in physics, really.
All right, so break it down for me. What does that even mean?
In the simplest terms, it means that the total momentum of, say, like a closed system, it stays the same. It remains constant, even if the momentum of those individual parts within the system, they change.
Okay, I think I get the concept, but can you give me like a real-world example?
Sure. Imagine a game of pool, with the balls and everything.
Oh, yeah.
Okay. Each ball has its own momentum as it zips around the table, right? When two balls collide, their individual momentum changes. One speeds up, maybe the other slows down, they change direction. But here's the thing. The total momentum of the whole system, all those balls together, it stays the same before and after those collisions.
So even though it looks, I don't know, kind of random with the balls bouncing everywhere,
It's organized chaos.
there's like a hidden order to it.
That's the beauty of conservation of momentum. And, it applies even in situations that are way more chaotic than a pool game.
Okay, like
Or a car crash.
hold on, wait, a car crash with all the damage and the debris and everything. How can that possibly have the same momentum before and after?
You're right. Car crashes are crazy complicated. But that principle, it still applies. The total momentum of the cars involved right before impact will equal the total momentum after, even though the cars might be, a bit worse for wear and moving in totally different directions.
So even though all that energy is getting transformed, like into heat, sound,
Yeah.
the momentum itself is still conserved.
It has to go somewhere.
That is mind-blowing. Okay, now what about situations where it seems like momentum just like appears out of nowhere?
Like what?
Like a rocket launching into space,
Ah, yes.
going from 0 to thousands of miles per hour. It's incredible.
Rockets are a classic example of, I guess you could say, how we can outsmart momentum in a way.
What do you mean outsmart? Does it just like magically create momentum?
Not magic, but it's pretty close. The key is you got to think of the rocket as a system. By expelling that hot gas out of its engines with so much force, it's essentially, it's throwing mass in one direction.
Okay, I'm following so far. So by shooting out all that mass, like it's saying, see ya, the rocket itself gains momentum in the opposite direction.
Boom, you got it. It's like a trade-off, right?
Yeah.
Rocket throws mass one way, and to compensate, to keep that total momentum of the system constant, it's got to gain momentum in the opposite direction, which of course propels it upward.
Wow.
It's a powerful demonstration of how we can harness these physics principles, to achieve some pretty incredible things, like launching ourselves into space.
Yeah, no kidding. It's not magic, it's physics.
Better than magic.
Way better. Okay, this reminds me of that video we saw, where a scuba tank explodes underwater. It's intense. The tank, it just rips apart, sending pieces flying everywhere. Is that another example of conservation of momentum, even though it's, unintentional and dangerous?
Absolutely. It's a stark reminder that these principles, they're always at play, even when we don't want them to be. When that scuba tank bursts, the force of all that expanding gas throws pieces of the tank outward. Each piece carries a certain amount of momentum. And even though they're going in all different directions, the total momentum of that whole system still constant.
That's both amazing and kind of terrifying at the same time.
Physics, huh?
Physics. Well, this has been an incredible, truly incredible journey into the world of momentum. We went from everyday objects like baseballs, tennis balls, to some mind-blowing scenarios, rockets, exploding scuba tanks.
We've covered it all.
And through it all, this seemingly simple concept of momentum, it's been the connecting thread.
It's amazing, isn't it? Momentum, it's like it's woven into the very fabric of our universe. It governs everything. From the tiniest subatomic particles to, like you said, the grand movements of galaxies. Understanding it gives you this whole new lens to view the world.
Totally. Okay, before we wrap up, any final takeaways for our listeners about momentum? Anything else they should keep in mind?
One thing that I think is really important is that momentum isn't just about how fast something is moving. It's also about its direction.
Oh, right. We've been so focused on speed and mass, but direction plays a key role too. Like I'm picturing a sailboat, right?
Okay, yeah.
Tacking against the wind. It can't sail directly into it, but it can still make progress forward. That's got to be because of the direction of momentum, right?
Yeah, exactly. You're getting it. A sailboat, that's a perfect example of how we can manipulate the direction of momentum to get where we need to go. The wind blows against the sail, creates a force, and that generates momentum. But by adjusting the angle of the sail, those clever sailors, they can harness that momentum and move in a direction that's not directly aligned with the wind. So they can actually sail against the wind.
That's so cool. It's like they're, I don't know, borrowing the wind's momentum and redirecting it to get where they want to go.
Exactly.
This whole deep dive has really changed how I see the world. Seriously.
I love it. That's what we like to hear.
So to our listeners, keep that sense of wonder alive. Next time you see, I don't know, a game of pool, a rocket launch, or even just feel the wind in your hair, take a moment. Think about those invisible forces at play. That dance of momentum shaping our world in ways that are, that they're both subtle and profound.
Beautifully said.
This has been another fascinating deep dive. Until next time, keep exploring, keep questioning, keep seeking those aha moments.